Hello. This is going to be talk about Haskell, and it's not going to be one tutorial. There's plenty of those on the free links you can see on the slide, and they will probably only confuse you. So, in order to start working with Haskell, you need to emerge the Glasgow Haskell compiler and Cabal install. This is what hello world looks like, and it's a definition of function main, which calls put ctrl and hello world. And below you can see you can run it with run Haskell, and it prints hello world. Haskell is purely functional, so I have here an example that takes a list of strings, converts them to integers, and then decrements them by 1. You can see the main function that it's again _, which prints a string line. Then its argument is a call to show, which converts its argument into string, and then we call convert and the list of strings. And we are going to focus on the function convert. The convert takes one argument, x's, and calls map, which applies the breadth function to the result of another map, which applies read to x's, which is the list of strings we have. So it first converts the x's into integers, and then decrements them by 1, and it then gets converted back to the string and printed out. Below the Haskell implementation, you can see comparable implementations in Python, and the output it gives. It shows the list of one integer and second integer. The part with double colon and int, that's a type annotation for the read function, because read function can read strings into multiple, or rather different types, like int, integer, and float. So that's why it's there. And as it is purely functional, it focuses on functions a lot. So we can use application operator to get rid of the parentheses in the both functions, both the convert and the main. So these two programs are doing the completely same thing. Is this understandable so far? Or is there any question? Then we have composition operator, which we can use to compose two functions into one function. And here in the convert, we use it to get rid of the w's of mapping a function over a list which generates another map of functions on function on another list. So these are again the completely same. And below you can see type signatures of read, which is string to int. Then we have the predecessor function, which is int to int. And when we compose it, it just calls the read function and its output goes immediately to the predecessor function. So its type signature is string to int. Then we can use partial application to get rid of the argument to convert. Because in this code, we define the convert function to be map function with the composed predecessor and read, but it's missing an argument. So the argument will be filled from the same position in the convert. So this is again the exactly same program. Any questions? Haskell is fairly functional, but it can look pretty imperative. Here we have function main again with something called do notation, and this prints a question, what's your name, on standard output. Then reads a line into a name variable, and then prints the answer with welcoming you. No, I am not sure what exactly the arrow means, but I understand it as executing a computation, or rather input and output computation in this case, and binding its result into the left-hand side of the arrow. And below you can see the output. So this is yet again the same program, only I have replaced the actual functions in the main function with named ones. So instead of directly asking, we have a function ask, the getLine, which takes another variable because of what I'm going to show on the next slide, and the welcome. And it's still purely functional. So the do notation is only a syntactic sugar for taking these three functions and applying them in pipeline. So this executes ask and passes its output into the getLine. But the actual getLine we need to use does not take any parameter. So that's why we have the unused variable in the underscore getLine definition. And the result of the getLine, which is the red name, gets passed into the welcome function. This double arrow and equal sign, it's usually called bind operator, and it's operator on a monad. But I'm not going to get into this. It's basically a complicated way of saying execute left-hand side and pass its argument to the right-hand side. Any questions? Now, what you see in the line with the monad, that's the type signature of the bind operator. And if you have a function or an operator, in which case you need to quote it in the parentheses, and you don't know what its type signature is, but you want to know, you can start GHCI, which is an interactive Haskell interpreter, and type just :T and the name of the function or the operator. And as an output, you will receive the first line on the next on the next example, right below it. Head is a function that takes a list as an argument and returns only its first argument. And below we can see the equivalent Python implementation. And how it is implemented in Haskell, it's using pattern guard, which you can see on the second line. Actually, I can show. Here you can see the pattern guard, which is a way of saying that the head function takes a list, and you are interested only in the first element of the list, which says the x. Then colon and underscore would be the rest of the list, the tail. But since we don't need it here, it's using the underscore to express this intent. Now, this function is equal only to the x. Yes?
Are the type signatures of the functions, are they necessary when defining the functions, or are they just a way to supply?
They are usually, or rather often, not necessary. But as you saw on one of the first slides, here is a read function which I don't really know how it's implemented, but it is capable to read or rather convert strings into integers or floats or even different kinds of numbers. And in that case, you need to give it a type because it can't infer it automatically. And there are two definitions of head, and that's also part of using the pattern guard, because on the third line we are handling only the case where the list given is empty. So in that case we print an error that says that it's an empty list. And below is the equivalent. I already said this. I'm not sure there might be an output, but also this type signature says that you are going to define a head function which takes a list of A's, which is I think type variable, and it means that it can be anything in there. But whatever you give it, you will also return. That's what the arrow and A says. You could take multiple arguments, and you could use type variables A and B, and those would be different types. So this way you would precisely define the type signature when having different types, but they could be anything. Now there's a cool thing named Google. So if you want to find a function, but you don't know how to find it, you still probably know what the function should do. So if you are looking for a function that takes a string and converts it into a list of words, that's kind of obvious that you are looking for words. But there are cases where it's not so obvious. So you can just use Google to search for the type signature you need, and it will show you that there are functions, or it knows functions that's called lines and words with the documentation. So you can find, you may find what you are looking for there. It also finds similar functions, which is string to file path, because file path is actually a string internally. And once we get into dealing, there are some more generic ways of splitting something into a list of something. And yep, there are also some monadic versions of it. So if you find a function you need to use, and it's in some kind of library, you need to import it, and it's as simple as asking for the import. But this actually imports everything from the module. Every symbol defined in the module, it will import into your program. That's right now we don't use any functions from that import. So it compiles fine and prints the same list we give it. And it's basically equivalent to this Python program, where you have again 2 modules and you import everything from there. But there's a problem that if you execute the main function, it will just silently use the latest imported function. And this compiled because we didn't use anything, so it didn't really import anything. But if we try to use sort, which is defined in these modules, we get an error in compile time telling us exactly what happened. So we can solve this in various ways. One of them is that we just hide the function we don't want. There's also a way of saying that that we want to import that module in a qualified way. That means we give it another name for the whole module, and then if you we could say import data sequence qualified as S, and then we would have to access the sequences sort function via s.sort. Any questions? So this is a way to define some more complex data, like you would define an object. So you say data, and then we want person. That's the name of the type, and equals person, and that second person is actually called type constructor, and I will get to that later. And that type is composed of a name field, which is a string, and surname field, which is a string. And deriving show is kind of magic. And show what show actually does is display the type as you would type it into the Haskell interpreter. So if we now ask to show the in the main function, we create a new object of type person, which is named John Doe, and we show it. So that gives us the string below, and that's just another way to create a new person object. This is roughly equivalent to the class below, but if we want to display the person in some meaningful way, we need to define the wrapper functions ourselves, and this is where the deriving show comes in. That's quite helpful. Here we have another data type, which is a color, and it has constructors red and blue, and it takes no parameters. So this is quite useful, as you can reference the color by a type name, and therefore making these colors type safe. So it's not possible to make a typo or use that object in some type incompatible way. As we see below, we are asking to show the red, but the program doesn't know how to do it yet, and this is how polymorphism works in Haskell. Show works on a lot of objects, and that's because it's a type class. It's a type class that says that it defines function show, which takes an argument and prints a string. That's the whole definition of the type class, which isn't shown here. It's in the standard library. But what we do here is that we are saying that we want to define an instance of that type class we want to define an instance of show type class for the data type color, where the show function, and this is where the pattern guards come in, where the show for type of color red, we want to print just red. And the same goes for the blue. And then we can just show red. Now, I think that if we did not define the blue here, the compiler would also complain that the definition is incomplete. Again, in compile time. So, let's make some packages. Here we have a program which imports module named Fibonacci, which is used to generate some Fibonacci sequence, the beginning of it. And if we just run Haskell it compiles and it executes, because we have installed the Fibonacci module on the system we are running it on. The system for packaging in Haskell is called Cabal, and this is how you define how you write a Cabal file. It's, for example, and this is basically a bunch of metadata about the package. Like it starts with metadata which are mostly free-form text, like the package name, version, authors, and various stuff. And at the bottom we defined that we want to create an executable view from then we define the file that actually implements the executable main function. Then we tell it to search it in the source subdirectory, where we placed the file, the default language, and build the dependencies. Now here we depend only on the base package, which is the standard library, and we get an error. In order to make a package, you need to call cabal configure, which does I have no idea what, and then cabal build, which actually builds the package. And right, we did not define that the package depends on the Fibonacci model, and cabal is capable of catching that. So even while the module is actually installed and accessible and the program alone works with it, the cabal will tell you there's a problem with the packaging. And this is how you fix it. Any questions? Right, and here we see the same thing, where we are trying to build the package, and the package executable is built under the directory dist build foo, which is here execute, and here we see the same correct output that we expect. Now, if you want to do unit test, if you have a function that you think needs unit test, and the type check is not enough, there's a nice library called hspec, obviously inspired by the Ruby unit testing library, and it's basically another executable Haskell program where you import the hspec module and then run and define the main to be magic hspec, the do notation, describe, string describing something, and again do and it something, and then you write the actual test where I'm testing that 2 + 2 should be 4. That looks pretty readable, doesn't it? And below we can see the output. The actual output is colored with greens and red, but I was unable to replicate it here. So here we see that works test case. Isn't failed, while the other one is failed, and I don't know why there is one, but it looks like it's an error. And it tells you what it expects and what it got, and some other stuff. Now, if you have an hspec, or actually any other kind of, or any other way of making a test suite, which is an executable program, you can just add these lines into the cabal file, which tells it what kind of test it is and how to execute it, and then you can run just cabal test. And I ran out of slides, and it appears I ran out of time as well. So any questions?
Can you list some major projects that are coded in Haskell, like some success stories?
Xmonad is written in Haskell. It's a tiling window manager, which is pretty cool. I think some financial institutions are using Haskell for high-speed trading or something like that. I know some are using some kind of ML as well. And I can't think of anything else. Any more? The coolest thing about Haskell is that it helps you with catching errors early in compile time. So you don't have to write tons of unit tests just to catch typos and various silly errors. And if you make a type error, it can't happen to you that you will deploy it in production. So thanks for listening. Have fun.